as a confirmation. Yes, we'll get going here. I want to thank everyone that's taken the time out of their day to spend about an hour with me. Hopefully, I can bring it into the hangar a little ahead of time. We've got a really good crowd this afternoon, and I'm excited about this topic. So, we're going to talk about a couple pieces of ruminal acidosis, and we'll talk about rumen function, mostly about feed degradation and nutrient use, and then connecting that story to the cow's broader systemic inflammatory status. And there's a lot of interesting data that I have today. Some of it is going to be applied in nature that I really hope you can take home and use right away. And some of it, I really just want to challenge you to think a little bit about what are the opportunities and challenges within the rumen that we're not thinking about. And that's across species. That's small ruminant, beef cattle, dairy cattle, whatever it may be. So that's going to be the mix for today. So I'm really looking forward to the interactions and really looking forward to hearing what everyone else has for thoughts when we get into the rumen and the mystery world that exists there. So we will get started. As I said, we're going to step through this one step at a time. We'll start with connecting rumen acidosis and nutrient degradation, which is some of the more classic research. Then we'll get into a little bit more of the recent stuff that I'd say has been done in the last decade and even the last couple of years. Um, the exciting parts that I will get to at the end, I think will really open your mind to be thinking about what the rumen is doing in a little bit of a different way. And then finally, we'll talk about what we're learning here at Ohio State and what my team is working on. I see one or two of the students is actually on the call. So if I go long, it's because those students have been creating too much good data to share. So blame them. They deserve a lion's share of the credit there. But with any discussion about the rumen, I think we really need to start with the fundamentals. And so if you've seen these figures before, forgive me, but I want to make sure we're all on the same page. It's important to understand the structure of the rumen is very unique compared to many other gastrointestinal organs. It is a stratified squamous epithelium. So that just means it has layers with different shapes that are all smushed together, right? And the top one, the layer that's facing the rumen fluid, the luminal surface, is the stratum corneum. That's going to be a layer of dark cells they're dead, basically. They're squashed, they're anucleated for the most part, which you can see. That's the piece that's interacting with that rumen fluid. Then as we go down, we have the stratum granulosum, spinosum, and basal. And as you'll see, as you move down, the shape changes, and we also get more mitochondrial functions and more cell functions as we head down towards that basal layer. What I will get to at the very end of this seminar is that this is actually an incomplete model, and there's a few other cell types that we need to make sure we're including when we think about the rumen that are probably critical to how that rumen is regulated. Now, how does that compare to the hindgut? And the reason I introduce this is because we will try to shift the discussion a little bit from just thinking about the rumen as an isolated organ to remembering that it's part of an entire GI tract. And we need to understand that hindgut, lower gut as well, and see what's going on there and how that may affect the cow. So important to remember, we have a single layer of epithelial cells in the intestine. Columnar cells in this case. Now, there's a diverse type of cells in the small intestine, less so in the rumen that we know, but a very diverse type of cells with two mucus layers. One that's an inner mucus layer that's really tightly bound, one that's an outer mucus layer that a lot of stuff can live in. And this will be populated by different peptides and enzymes. And the small intestine and certain segments of the intestine are immune cell rich. They have a lot of immune functionality, and the gut is becoming recognized as one of our largest immune organs. So that's important to remember when we talk about animal health and the inflammatory response to diet. It wouldn't be a ruminal acidosis seminar if we weren't going to sit here and talk about definitions of SARA or subacute ruminal acidosis. Most of these definitions that I think many of you will be familiar with rely on a cutoff or threshold of rumen pH and an amount of time spent below that threshold. In general, we're talking 5.8 to 5.6 for a subclinical bout with more than 3 to 5 hours a day spent beneath that cutoff. This isn't necessary. It doesn't necessarily mean that cows will do terribly if they're experiencing SARA based on these thresholds. As I'll get into some of the next couple slides, SARA and acidosis is more nuanced than that. There's a little bit more going on that maybe we should think about. But the prevalence of SARA based on these kinds of measures ranges from 11 to 27 up to 33% on one estimate that jumps to mind. And that really depends on management system, grazing versus confinement, diet, stage of lactation, a whole slew of things, as you'd expect. In this study, these Otzel 2004 and Golder 2023, these are largely confinement dairies. That would be a U.S. North American style farm or operation. I put this one in green mostly to remind me that it was a study, an Irish study, if I'm not mistaken, that did pasture or grazing, and that was an 11% prevalence. So a range of prevalence, but just taking home the idea that these low pHs do occur every day on farms. That's not meant to say we have a huge problem. It's meant to illustrate that this occurs often, and we need to understand it better to make sure we're addressing the problems where they lie and not where we think they exist. Now, what are the problems that may coexist with low rumen pH and subacute acidosis? The big one that, as a nutritionist, I worry about, and from an efficiency perspective per unit of resources used, is that ruminal acidosis is generally associated with reduced fiber digestibility. And you'll see that on this slide here on the right, where they gave a cow acidosis. They put grass hay in there and did an in situ degradation. They found the cows that had Sarah had a 13 unit reduction in NDF digestibility. From a nutrition perspective, that's enormous. That is such a big response and something we don't want to happen, right? The cow's niche is to digest and use fiber to make protein. So we want her digesting more fiber, not less. So that's one of the things that's important to remember about Sarah, and I have a bit more data on that as well. There's also an altered ruminal microbiome. I want to preface my comments on the microbiome to remind people I'm not a microbiologist or a bioinformatics microbe person. I'm learning in that space. I'm trying to catch up on the literature of all the gazillion species that exist there. We'll talk a little bit about it, but not a ton. But just know, yes, we do have an altered microbiome with reduced ruminal pH. We also have an altered volatile fatty acid profile, which is super important to understand because that changes the entire energy substrate profile that that cow is going to get. And finally, from the inflammatory perspective, we get an increase in lipopolysaccharide within the rumen, which on itself maybe is not a bad thing. It's the microbes lysing, releasing this LPS, but it can interact with the rumen epithelium and cause some problems. And then finally, biogenic amines are another compound that can also have some inflammatory capabilities when interacting with different cell types. So that's the 30,000 foot view. And I think the part that we've started to talk about more or think about more is, what about this generalized inflammation in response to rumen acidosis? So there has been more research in this area. There has been a lot of investigation, but it's really nuanced. And as you dig in, it's kind of interesting. And we'll get to that. But I want to start with rumen function and some of those basic rumen characteristics like feed degradation to really drive home the point that Sarah still has practical concerns from an energy perspective for the cow and from a feed and nutrition perspective. As we said, Sarah depresses ruminal NDFD, and there's a couple pieces to this. So first of all, this is a different study than the one I showed previously, but another ruminal in situ incubation. And they incubated 3 different forages. And in each case, we had a dramatic reduction in the 48-hour NDF digestibility when cows had a reduced rumen pH because of Sarah versus cows that did not. So then as a scientist or as a critical thinker, we sit here and pause and be like, okay, what's the root cause of that? Because now we know that, or we already know that reduced rumen pH leads to an altered microbiome population. Or is it the reduced rumen pH all on its own that's influencing this reduced fiber degradability? Well, unfortunately, it is probably both. This data is from an in vitro study published in Animal Science, and it's an excellent illustration that pH does independently reduce fiber degradability. So as you see on the horizontal axis, we have a range of pHs from 5 up to 7, and you can see NDF digestibility or digestion is on the vertical axis. There's 2 lines here. This lower line is a high concentrate diet. This upper line is a high forage diet. And the main takeaway here from these authors is that as we reduce pH, we do independently reduce fiber digestibility regardless of diet. So yes, the microbes that degrade fiber do poorer at a lower rumen pH. But you'll also see these lines have some separation. The diet and the inherent ingredients also matter, right? And so this high concentrate diet, we had a depressed fiber digestibility at the same pH compared to the high forage diet. So both of those things can be related to reduced fiber degradation. Now, this issue of carbohydrate composition with high concentrate diets has become clearer as we were able to model things as more data emerged. So this is from NASEM 2021, the Dairy Cow Nutrition textbook. And we were able, I wish I was on the committee, wasn't on it, but they were able to model the effect of starch on NDF digestibility because the database had grown to a point where that was feasible. And what they found is that for each unit increase in starch, you'll see that we have a negative slope. So starch being on the horizontal, fiber digestibility on the vertical. For each unit increase in starch, we lost 6/10 of a unit of fiber digestibility. So that's another thing to remember here is it's not only pH, but it also does seem to be the carbohydrate profile that can depress fiber digestibility. So if we feed more starch, we might get ruminal acidosis. That reduction in pH may depress fiber digestibility, but also the fact that we provide additional starch also may depress fiber digestibility. So it's a complicated picture, a little bit of a balancing act, if you will, when we're trying to figure out what is the root cause of losing that fiber degradability in this case. And a little more detail on the microbes as that they're the ones acting to degrade the feed, right? We want to make sure we know what they're doing too. Well, pH on its own reduces some popular or increases certain populations like Prevotella, Proteobacteria, and E. coli. The E. coli story is actually really interesting. There's a group from Canada that did some excellent work with ruminal acidosis challenges, and they found that in the rumen, when we do ruminal acidosis challenges, we get an increase in E. coli population. But then they went a step deeper and another step deeper yet, which was it was an E. coli population that was increased, but then within that, it was a highly pathogenic E. coli population that was highly adept at adhering to cells. The thought being that that may be leaving us at greater risk for acid or inflammation when feeding these high grain diets. I haven't seen that data replicated, and the inflammatory responses you'll see as we get into it isn't always occurring. So there's some neat stuff that we need to think about. But from a microbes and fiber digestibility perspective, we need to step back and realize that it's not only the microbes that are changing, it's not only the pH environment that we need to consider. Dr. Firkins, a colleague of mine here at Ohio State, wrote in a recent review that more research is needed to explain differences among microbial populations and their expressed cazymes, which is just a phrase for carbohydrate enzymes, excuse me, as affected by pH independent from other changes in substrate growth and factor concentrations. So we need to really peel back the layers that are going on in the rumen to enhance fiber digestibility and rumen function when feeding cows with high energy diets that may put them at risk of a reduced rumen pH. So there's a lot of pieces going on. I wanted to introduce those though to set the stage for how complicated this situation is. Now we'll get into the part that I think is a little more novel and that we think about a bit more often in a gut health perspective. And that is rumen acidosis related to inflammation? And it's a good question. It's one that there's some data to say yes, there's some data to say no that we'll walk through. But the part I want to send you home with for starters is that gut health, as a broad term, is very nebulous. We don't really know what it means. And frankly, we're still learning how to measure it for dairy cattle. We're still learning what different markers mean. We know we can do gut permeability or we can measure systemic blood markers that tell us this or that. But whether they indicate epithelial gut changes that are problematic, I think remains to be seen in some cases. So we have a lot of work to do there, but we're making it, or we're coming a long way. I think the people at universities that are doing some of the excellent cutting edge work have really moved the needle in the last 5 or 6 years. And that's the work I want to walk you through here today. So the first part about studying something like acidosis is can we reliably cause it? And can we measure that we've caused it so that we know we're doing something that we can then address? And there's two different models for causing ruminal acidosis that are generally used in the literature. And I bring those up because it'll get into another point I have about feed bunk management. But to start with, the classic acidosis challenge model is a grain induction, where we'll feed a standard diet, pretty stock lactating cow diet for the North American part of the world, where we're going to feed about half the diet is forage, about 26% of the diet is starch, but then suddenly one day we switch those cows to a higher carbohydrate diet or a higher starch diet where we take out some of the forage and we put in some wheat and barley, which is very rumen degradable. And that predictably reduces rumen pH, as I'll show you in a moment. The other model, which is really interesting to me because there is discord between these two on the experimental results side, is that we can step up cows slowly onto a diet where we replace whole alfalfa with alfalfa pellets. And we do that stepwise. We can still achieve that predictable reduction in rumen pH, but we get different outcomes on the inflammatory side that I'm going to show you. So to begin with, both of these models, the alfalfa model and the grain model, increase ruminal LPS, one of the markers for subacute ruminal acidosis. As you see in this panel, both of them also increase Both models also increased the time spent below 5.6 to a subacute ruminal acidosis threshold. So we do cause ruminal acidosis. We do get a depression in rumen pH in both of these models, but they don't lead to the same cow response on an inflammation side of things. When we look at the alfalfa model, and haptoglobin is the acute phase protein of interest. That's a protein we generally consider to be, it's a positive acute phase protein, or it increases during the acute inflammatory phase. So we consider that a marker of inflammation. When we're doing the alfalfa challenge model, where we slowly stepped up those cows, we did not have an increase in plasma haptoglobin, suggesting we didn't have a systemic inflammatory response or a gut health issue. When we did the grain challenge, or we being Cafapor et al., when they did the grain challenge, we go from nearly undetectable levels of haptoglobin to over 500 micrograms per milliliter, which would be above what we consider a high risk threshold for a transition dairy cow. Now, those two changes led people to think that it's not so much acidosis, but it might be the grain and the acidosis together that are causing this inflammatory issue. Now, this doesn't always happen. There have been a couple acidosis challenges that don't get inflammation or inflammatory responses based on positive acute phase proteins, but this is one indication, and I want to use it to set the stage. So there does seem to be differences in these models. And as more data came about, these authors took a good effort at trying to summarize if there's a break point or a cutoff when grain and concentrates become an issue, and that acidosis can lead to these increases in positive acute phase proteins. And what they did is lumped together a bunch of studies to do a fairly simple meta-analysis with a broken stick model, where they're trying to find where is the break point where these measures will increase. In this top panel, we have ruminal LPS. In this middle panel, we have plasma haptoglobin, an acute phase protein. And in this bottom panel, we have serum amyloid A, a different acute phase protein. And what they came home with was that once that diet hits 45% concentrates, we seem to have an increase in our inflammatory biomarkers for inflammation. So, if that was true, or if that was the case, that would be a huge problem for many dairy producers in confinement type settings where they're feeding diets in excess of 50% concentrates. Are those cows actually at risk for inflammation? If they are, we have a problem we need to think about. The caveat to this data is that it is mostly challenge experiments. It's mostly experiments where we were purposely trying to see if we could cause a problem by suddenly changing the diet. So if you go back to the data I was showing you, we had one model that slowly stepped up those cows and allowed them to adjust to the ration. And then we had one where we suddenly changed it on one day. That sudden change is confounded with the model, but that sudden change, that's the group that had the inflammation occur. That steady step up group didn't have the inflammatory response, which leads me to believe that feed management is probably part of the issue when we consider the inflammatory response to diet change. And there's another study that illustrated that. This is from Ohio State, well before I got here, but from Gott et al. 2015. The study was led by Dr. Weiss at the time. And they had three experimental groups, and I really like this study as an example for feeding management and its importance. But they had a low starch control at 24% dietary starch. They had a high starch control at 28. And then what they did is they mixed in acidosis challenges on one day each week, about 2 weeks apart in this case, where they spiked up the starch by dumping in a little extra corn or wheat and barley to see what would happen to those cows. From a practical side, what I really like about this is it reminds me of that weekend feeder that you bring in, or maybe they work 1 or 2 days a week and they were out too late the night before and they come in that morning to feed and they're asleep at the wheel, so to speak. And of course, they added the right ingredients. Of course, everything went perfectly. You don't need to worry that the cows were getting the diet we balanced for them on paper. So that variability at the feed bunk could be part of the story. And what this author saw when they measured one of the acute phase proteins that we've talked about so far is that when we do that sudden increase in dietary starch, that sudden increase in, or that sudden abrupt change, we do get a little blurb on the radar for this acute phase proteins, serum amyloid A, when we do that SARA diet. So it doesn't seem to be just the diet nutrients, but it is that feed bunk management as well. So that's where, when we're talking about SARA and we're talking about the inflammatory aspects of SARA, the diet management and the feed bunk management needs to be a critical part of the story. To this point, I've been showing you scenarios where we either purposefully challenged the cows and purposefully messed up their rumen, or we purposefully screwed up the diets and surged some starch into the diets. After seeing all of that, my PhD advisor and I were sitting back looking at that data thinking, you know what, we need to summarize in regular feeding scenarios what's going on here. And we had some questions. So we wanted to look at, does increasing starch increase inflammatory biomarkers in cattle? Does starch in the hindgut increase inflammatory biomarkers in cattle? And is there a clear cutoff that we should consider as a take home for field nutritionists and veterinarians? And this is published in Journal of Dairy Science Communications. The title is here with some of the information if you want to go pull it out. Quick 5-page paper. I think it's a nice little paper. And the bottom line, though, as we go through that, is we were unable to pull out a consistent response to systemic inflammation when feeding dietary starch. So this is those two same proteins we've been talking about. Haptoglobin here on the left, serum amyloid on the panel on the right. And you have a slew of studies across the bottom. These were not acidosis challenge studies. These were studies feeding different levels of starch in the diet, where they were fed what I would consider adequately, managed well, fed at the same time, fed with bunks being pushed up, and fed for about 5 to 10% refusals, depending on the study. But what you'll see is that there is no clear pattern that emerges here. So for haptoglobin, for example, this green study, McCarthy et al. 2015, they go from about 600 haptoglobin micrograms per mil up to over 900. You look at that and you're like, wow, that's a problem. Starch caused inflammation in a transition cow. That's terrible. But when you dig into these other studies, that result doesn't seem repeatable. We have some studies that tend to go down, tend to go up, tend to go down, tend to go up, tend to go down, relatively flat. The other thing I should mention is the dotted lines are statistically significant, solid lines are not. But when you come down to it, there's no discernible pattern. If we look at serum amyloid A, same thing. If we increase from really low to really high, we had an increase. In these cases, within those higher levels of starch, it wasn't substantial. But we have more work to do in this area. And so we looked at this data and we're thinking, okay, first take home is feeding starch to a transition cow or to a lactating cow is probably not going to dramatically shift her level of inflammation that's occurring. But there's a lot of sources of variation that we should consider. It's the rumen flora that we don't understand. It's the rumen tissue adhered microbes that we don't know much about yet. Those microbes that are actually interacting with the rumen tissue, those might be different by population and need to be considered in this animal's inflammatory response. We have the hindgut microbes that we know very little about in a lactating dairy cow. What about the level of intake, physiological status, heat stress? We have so much we need to learn about the sources of variation within these study and about what can be affecting these cows' inflammatory response to diet. So, as I said, I want to try to broaden it from subacute ruminal acidosis to thinking about the whole gut. And some people will call it SAGA or subacute gut acidosis. So I put that up there as an alternative acronym. But we need to be thinking about, is it the rumen? Is it the gut? Is it both? Is it neither? And again, when we think about what's going on in the intestine, this is review from the beginning of the PowerPoint, but we have two very different structures. In the rumen, we have these big papillae with a multi-layered epithelial structure. With at this point, we don't believe any mucus in that layer to protect it, but with that stratum corneum, that layer of dead cells to provide protection. And as we move through that GI tract, we get a mucus layer that thickens as we get towards the rectum. We get cell populations that are changing, immune cells that are actively surveilling the environment. And we also have the output of rumen fermentation that will flow through the intestine. And we need to decide whether that's problematic or not. So, what does the data say about hindgut acidosis? In the last 3 years, last 5 years, there's been a pile of data published in this space, and it has been really fun to dig into. So we're going to go through some of it here. First of all, we can reliably reduce hindgut pH as a model of hindgut acidosis. These two studies are from the Netherlands. Sanne van Gastelen is an excellent scientist there in the Netherlands and did two starch infusion projects. And then there's a series of projects out of Iowa State and Dr. Lance Bumgard's lab with Megan Abeda as the leading PhD student on that work, where they infused either purified cornstarch or corn grain between 3 and 4 kilograms per day into the abomasum. So we're bypassing the rumen entirely. And we do get a reliable 1 unit reduction in fecal pH, going from mid sixes or around 7 down to as low as 5.1. So those are huge reductions in luminal with an L, pH, which if we're in the rumen and you told me you reduced the rumen pH by a whole unit, I would wonder what you did. So these are big shifts. These are not small shifts we're causing in this model. So the thought is that it's not the rumen that's the problem in these cases. It's the hindgut that might be getting overloaded with starch, having an acidosis response, and having an inflammatory about. But did these guys in their studies, or gals in this case, did they get an acidosis and inflammation response in the hindgut? No. In each study, they measured an acute phase protein or an inflammatory biomarker. Different ones across studies, so it's kind of hard to compare. But in none of them did they observe an inflammatory response based on acute phase proteins from the additional hindgut starch. Now, they had in the Van Gastelen studies, they looked at, I believe it was haptoglobin. I don't remember off the top of my head, but again, no response. Across the Abeta studies, they actually did some interesting stuff where they were doing stacked stressors with LPS or with heat stress or in early cows or late lactation cows to get a broad context of animals. But in none of those cases did the starch provide an additive effect to the inflammation that may have already existed. So we have no evidence that the hindgut acidosis is related to a systemic inflammatory response. There are limitations to that, though, and we'll get to that in a minute. The interesting part is in two of those studies, in both the studies in the Netherlands, they also looked at fecal VFAs. And what I found interesting is that in both studies, when we give cows the hindgut acidosis, the starch straight through into the abomasum, we dramatically increase fecal butyrate. So on the left, we have the control groups from both studies. On the right, we have the acidosis infused groups or the grain infused groups. And we get a doubling in the proportion of butyrate in the feces. So what I think is interesting about that, that clearly demonstrates that the flora in the hindgut and the rumen are different. They're going to metabolize starch in a different fashion and have a different outcome. The other really neat part of this is butyrate has immune signaling functions. It alters immune cell function, cytokine production, phagocytosis, and can have effects on gut permeability and gut structure. And so that's why this result is so compelling to me, is because if we can understand the hindgut metabolism, we can understand the outputs there, we can perhaps understand ways to maintain a really vibrant, healthy lower gut in these cows. But with the data we have to this point, it doesn't seem like hindgut acidosis is a problem to be that a problem that is causing consistent inflammation in high production lactating dairy cows. The limitations on this data, though, that I think we need to really hammer at is these studies were very short duration. They weren't going to feed these cows and infuse them for start with this starch in the hindgut for 90 days or 100 days or even 300 days, like a cow might experience during lactation. Very short duration of exposure. So it very well may be that these 3-day, 7-day, 10-day studies are not enough to compromise the lower gut epithelium to the point of a systemic inflammatory response. So we need to keep that in mind. Also, when you're bypassing the rumen, with the starch, you are completely eliminating any other ruminal compounds from that fermentation, whether it be LPS, biogenic amines, volatile fatty acids, or the microbes themselves that are going to pass through to the intestine and could have interactions with the gut epithelium to cause an inflammatory response at that tissue level. So a lot of things we don't understand, a lot of limitations. But when you summarize it all, grain challenges in the rumen where we slug them with starch, we do get an inflammatory response most of the time or some of the time. That is accompanied by reduced rumen pH, increased LPS, increased E. coli. Okay, when we infuse the abomasum with starch and bypass the rumen to cause hindgut acidosis, we do not see an inflammatory response, but we do see an increase in fecal butyrate that I think is interesting and perhaps worth exploring. Then finally, if we're just feeding greater starch with a well-managed bunk to early and mid-lactation dairy cows, we do see a reduction in rumen pH, sometimes an increase in the occurrence of subacute ruminal acidosis, but we do not see a generalized inflammation response that's consistent. And what needs to be borne out, I think, more is do we see that butyrate response when we feed cows normally and are not bypassing that abomasum in an experimental setting? Because again, butyrate can have some effects on the gut epithelium and immune cells within the intestine. So that I hope was a fairly comprehensive background of where gut health stands right now. And that leaves me about 15 minutes to get through the stuff we're doing at Ohio State. So I knew this was going to be a concern, but I'm already talking too much. So I'm going to move a little more quickly in this second half. First of all, when we're investigating anything in nutrition, in this case, we're talking about starch and degradable carbohydrates. The goal should be to find the optimum concentration that serves that animal's purpose for whatever you're trying to accomplish. Whether performance is milk yield, or performance is pregnancy, or performance is average daily gain and carcass weight, there is likely an optimum. More is not always better. At some point, there will be a break off, and those cows won't do as well. So we have to consider that. In the case of starch, and degradable carbohydrates, if we don't feed enough of them, we're likely missing out on milk production, especially milk protein production. But if we overdo it, we're likely getting milk fat depression, ruminal acidosis, which means depressed fiber degradability, and perhaps are we getting an inflammatory response as well? Hard to say. So some of the data on feeding starch to cows that I wanted to throw in here just for the additional context is that when we go up to about 30 to 32% of the diet starch, we do generally see an increase in milk protein when we're replacing fiber. This was a study I did at Michigan State with Dr. Bradford, and we increased starch from 25 to 30. We had an 80 gram per day increase in milk protein yield. In a study from 2015, also done at Michigan State, Borman et al. Saw an increase of 100 grams a day when they went from 16% starch up to 31 or 32. So starch can drive milk protein yield and profitability, in this case, increasing revenue by 40 to 60 cents per head per day based on the market prices. But that's where we need to determine, is there a break point where too much starch is, or where that additional starch becomes a bad thing? And so we did an acidosis challenge of our own, where we wanted to understand where these breakpoints may be. And the main thing to pull out of this table is that we had a pretty traditional lactating cow diet, 24 forage NDF, 27 starch, and our Sarah induction diet, where we pulled out forage, put in wheat and barley, much like the previous experiments did. Fully expecting cows to go to get actually a clinical acidosis because we added so much wheat and barley. We were expecting a fairly severe response. We didn't get one. We actually saw cows increase in intake when we provided the additional grain, and we saw them increase in milk yield and milk protein yield, just as the book says. We didn't seem to cause a severe enough acidosis response, even in this challenge setting. So that again is where context dependent and a lot of unknown variables probably affect these cow outcomes. But even with this response, did we have some rumen issues? Did we cause subacute ruminal acidosis? Well, we did. Initially, we had a relatively low rumen pH to begin with, about 5.9. When we added the grain, it went down to 5.7. So 2/10 reduction is fairly substantial in that setting. We also reduced the maximum fecal pH from 7.2 to 6.9, but the average fecal pH was pretty much the same. So fecal and hindgut dynamics do appear to have shifted a touch, and our time spent beneath 5.6 went from just under 2 hours to 3.5, almost 4 hours. So we did seem to cause that subacute ruminal acidosis. But did we change the rumen epithelium? Did we cause damage? Did we cause systemic inflammation? Well, we did cause palpable changes in that rumen tissue epithelium. We had on the 26% starch diet with corn, you can see the rumen papillae that seems fairly well organized, fairly vigorous and hardy, no breaks in the outer sternum corneum. But then when we fed the additional starch and added more wheat and barley to the diet, we didn't dramatically damage the stratum corneum or damage the tissue, it appears, but we did have a thinning of the stratum corneum by about a third. And this inner layer, this basal layer, expanded by about a third relative to the entire papillae. So there are structural changes that occurred, and this occurred within 3 days of the diet switch. So it was fairly quick. So first takeaway there is cows do respond to diet, and the rumen will respond to diet from a tissue perspective rapidly. But are these indicators bad things, good things? Is it a sign of a tissue that's turning over more quickly? Is it a sign of a tissue that's stressed? That's the part we need to understand. In this study, we did look at inflammatory biomarkers, and we looked at haptoglobin, lipopolysaccharide binding protein, serum amyloid A, and D-lactate, none of which were substantially increased as a result of diet. Haptoglobin had a slight increase here from day 2 to 3, but nothing worth writing home about, frankly. And we left that fairly surprised. We were expecting an inflammatory response that was indicative of poor gut health, but we didn't get that, and it's really changed the way we think about this challenge. But when you dig into the data further, and this is where, as scientists, sometimes we might get stuck on a mean, but we need to look at the population and maybe go individual by individual. And in this case, it was a small study, so it was easy to do. We only had 9 cows, which are listed here on the bottom. But one of these individuals did have a spike in that haptoglobin level after the acidosis challenge. So there is likely something at that individual level that might leave that animal at greater risk. So there's something worth being understood there, but we are still trying to decide what direction to take that. When we looked at tissue, so I showed you blood biomarkers of inflammation. We did look at tissue biomarkers of inflammation with mRNA transcripts, and we did see some shifts. A reduction in IL-1 beta, which was surprising. We expected that to increase as that is a driver of the inflammatory cascade. And we actually had this increase in IL-10 and IL-17, which is intriguing. IL-10 because it generally is considered to be a pro-resolving anti-inflammatory transcript, and it was increased in rumen tissue. And IL-17 appears to be very important in the gut and context dependent of whether it's a pro-inflammatory pathological cytokine or whether it's a resolving and tissue helping signal. So there's a lot of noise to that. But again, this was driven largely by two individuals that had big changes in their transcript abundance. So that individual level variation is something we need to dig into. But what I was really excited with is this study, I believe, confidently established that we have an immune cell population within that rumen tissue structure that we haven't given enough credence to in the past. And in this case, we did immunohistochemistry, and there's little red dots and green dots that are co-expressing two cell signals. And I pointed out two of them here, but what those are T cell markers that are being expressed or highlighted, demonstrating that within that rumen epithelium, we seem to have T lymphocytes. And the question then becomes, are these T lymphocytes contributing to that regulation of the rumen tissue? Good question. We think they are, and as we go through this data, I think you'll see that there is the opportunity, or that the data so far does suggest these cells are having a signaling effect. So we did an additional study. This one is not published yet. It's actually was submitted to Journal of Dairy Science yesterday, I think. So hopefully it'll be coming out this calendar year. But we did a low forage diet. Wanted to stress these cows a little bit, see what that rumen did. And 12.6 forage NDF, but then we increased starch from 23 to 33% of the diet dry matter to see if we cause issues with that rumen epithelium, see if we challenge that gut health, as we all like to refer to it. Now, what did we see? Surprisingly, as we increase starch, no change in rumen pH. In these low forage diets where cows are consuming a high volume of degradable non-forage fiber, the rumen pH was already depressed. The addition of dry ground corn in this case, by increasing starch, didn't cause any further reduction in rumen pH. Now, it was low to begin with. These cows spent roughly 5 hours or 6 hours beneath a 5.6 pH. So the pH was low. It would be described as subacute ruminal acidosis, but it wasn't made worse by additional starch in this low forage setting. We did not see any change in fecal pH as a result of increasing dietary starch. So it's just because you see a shift, or if you don't see a shift in ruminal pH, you likely are not going to see a huge shift in fecal pH, it seems. But fecal pH also is not the most sensitive marker when you're feeding cows, but we're having a hard time finding a better one to get an idea of hindgut fermentation. But now, so we've set that up is we had this no change in rumen pH, no change in fecal pH. We dramatically increased dietary starch. Do we have inflammation occurring? And when we looked at blood markers of inflammation, acute phase proteins like haptoglobin and lipopolysaccharide binding protein, we looked at plasma cytokines. We did not see any response to suggest there was a systemic inflammatory response. But what we did see is that we seem to have a tissue level inflammatory response. Now, I partnered with some folks at the med school that took some rumen tissue, isolated the protein, and did a cytokine analysis of the protein from the rumen tissue itself. And what we found was an increase in interferon gamma, an increase in IL-1 alpha, an increase in IL-4, and an increase in IP-10. Each of these cytokines seem to find their root going back to a T cell. And within the signaling networks of some of these cytokines, especially interferon gamma and I believe it's IP-10, they're intertwined and go back to a T lymphocyte. So this data starts to suggest that maybe those T lymphocytes within the rumen are changing their signaling in response to different diets and whether that's causing a tissue level inflammation or not. So here we have some preliminary investigation to say that when we increase starch in this particular context in a reduced forage ration, we do seem to have an increased inflammatory response at the tissue level. So from an applied perspective, feeding cows in that low forage setting, for now, we can say that a reduced starch ration will leave you at lower risk of inflammation when we have a low forage diet. Now, we did also do flow cytometry on this study on that rumen tissue to look at those different immune cell populations. And we again confirmed that there's a big T lymphocyte population. So at the beginning of the presentation, I said some of this stuff was going to get to be a little more basic biology, but I wanted it to open the minds and get everyone thinking and try to get creative about what this could mean. But we do seem to have a T cell population within the rumen, most of those being gamma delta T cells, which is really curious because those T cells seem to have a regulatory function. They seem to really help control inflammation so that it doesn't get out of hand. So I think that's really interesting to look at. But we do have T cells. We do seem to have tissue level inflammation as starch increased. How did the cows do performance wise? What happened when we increased starch? For these cows? Well, first thing on a low forage diet to high producing cows, they ate a ton. They ate 35 to 37 kilograms of dry matter. Just ate us out of house and home for this study. But as we increased starch, we did experience milk fat depression, going from a 3.9 milk fat all the way down to a 3.3. But as I said previously, starch usually is a way to increase milk protein. But in this context of a reduced forage ration, that didn't occur. We actually reduced milk protein concentration and reduced milk protein yield. And that's likely because once you dig into the literature a little bit more, you'll see that there is a break point for microbial protein production when we reduce forage or increase other carbohydrates. Around 30 to 35% of the whole diet is forage, which is what our study was. Microbial protein efficiency falls off. And that's what I think occurred here is in these reduced forage rations, although the cows are eating a lot, they have a lot of fermentation going on. That doesn't mean we're getting all the microbial protein that we think we're getting. So in this case, we actually had a reduction in the milk protein yield. Energy corrected milk then was greatest on those reduced forage rations. So in this low forage setting, the reduced starch diet seemed to work quite nicely. So what can you take home from this as I try to bring this into a landing here? Again, when we look at that, find the optimum concentration of starch. How do you move that optimum to the right? How do you give yourself more chances to increase the starch in the diet and increase performance? Well, increasing the use of dietary buffers, increasing the use of yeast can also help maintain the rumen environment and managing the feed bunk well. As I said, the data I showed at the beginning really suggested to me that feed bunk management is critical along with the nutrient composition, and that if we screw up the feed bunk, that's when we put those cows at risk of a stress or an inflammatory response. Or conversely, the data I just showed is if we have a low forage NDF, we move that optimum starch to the left. If we have a low effective fiber, we move it to the left. If we have a hot diet with degradable starch, we move it to the left. So again, the way I describe this is buying insurance is if you buy insurance by feeding buffers, yeast, and managing a bunk well, you can shift that curve to the right. How do you buy insurance? I gave you a couple of them, but also having quality forages, hygienic forages, void of mycotoxin, managing a bunk really well, keeping feed in front of those cows all times a day, a well-maintained mixer wagon that presents a properly mixed diet to those cows, supplemental yeast, as I show you here with data from Desnoyers et al. 2009. Feeding yeast generally increases rumen pH. It can increase intake and milk yield as well. So it's something that I think is should be considered given that it's fairly cheap, something in the realm of 2 to 5 cents per day, depending on the product and whether it's live or not. And then stocking density. If we stock those cows really heavily and we feed them aggressively, the slug feeding risk increases, milk fat depression risk increases as well. So the take homes for you. Feed bunk management critical to rumen health. It seems that feed bunk management was almost more important than dietary components in causing that inflammatory response. Increasing starch in the rumen does change the rumen. We change that tissue thickness. We did seem to cause an inflammatory shift, whether it's good or bad, with some of those plasma or tissue cytokines that I just showed you. And the data also demonstrates that we're going to get a tissue response to diet change before we get a systemic response. So just because a study shows you no inflammation in plasma or no blood markers in plasma, we need to be considering what's going on at that tissue level as well. So to wrap up, I really want to acknowledge our sponsors and financial supporters. The USDA funded some of the work you saw here. Ohio Dairy Producers Association provided partial support for some of the research, as well as Purdue Agribusiness. This is our team. These are the students that do all the work. Kyrie Masiao, Tita Vandervoort, and Andy Majewski. Excellent group of students that I've been very lucky to work with over the last 2 years. And thank my mentors who've gotten me here, Dr. Bradford, Kononov, and Mamedova. With that, please follow us on social media. I do on that last slide you saw Ms. Vandervoort. She leads our social media effort and outreach. She does an excellent job. So please scan this QR code. and go follow us on LinkedIn, Facebook, and Instagram. And we also are trying to work on our YouTube presence as well. With that, I will leave it open for questions and hand it over to all of you. But this is my email. If you should ever need anything, feel free to reach out.